Our project was implementing and improving an existing study using recursive neural networks for factoid question answering. We have 5 members in our team: Camden, John, Akshay, Siddharth, and myself. Our project is based on a paper titled A Neural Network for Factoid Question Answering over Paragraphs. In this paper, there's a recursive neural network that was used to create features from quiz bowl paragraphs, and these features were trained with logistic regression to predict the answers to the question. And their algorithm is called Kanta, and we'll be referring to that throughout this presentation. The data is split up into history questions and literature questions, but our project focused mainly on the history side of things. A sample question is given below. One thing that's important to note that as you process each sentence, the later sentences in the paragraph give more clues about the answer. Also, sentences are prepared into dependency parse trees with existing methods, and we'll be going over those existing methods in this presentation. Each node contains a word, and each directed edge contains one of 46 dependency relations. Also, words, including the answers to the questions, are prepared into vectors with existing methods. Some baseline results that we achieved after training are: with Kanta, we achieved 60.2% accuracy on the test data, compared to Bag of Words with 35.8% accuracy on the test data. So it's quite a bit of improvement. Our projects will be divided into 5 main sections. Camden will present on port the feature creation RNN to TensorFlow. Siddharth on exploring different word vector representations for the RNN. I will present on alternatives to logistic regression for answer prediction. John will present on particle swarm optimization of the RNN, and Akshay on features beyond Bag of Words and the RNN generated features.
We were interested in looking at TensorFlow, which is an open source library roughly equivalent to sklearn, used for numerical computation through graphs. However, the TensorFlow documentation turned out to be about recurrent neural networks, not recursive neural networks, as are used in Kanta. And the general community opinion was that recursive neural networks really aren't a natural fit in TensorFlow. When every sentence has its own graph structure, you end up having to rebuild those graphs in TensorFlow for each sentence, and that's not efficient. The whole point of TensorFlow is kind of to build your graphs up front and then do all the computations very efficiently for static graphs. This was a neat opportunity to learn about recurrent and recursive networks, so let's take a brief moment to look at the two. In both cases, they're gaining efficiency by recycling edge weights, as indicated by the colored edges. The input are all transformed by the same edge weights into the hidden state, and then the hidden state values are all transformed by the same edge weights into the output. In the recurrent net, the hidden states are usually considered one memory cell, because each is feeding to the next in a straightforward fashion using the same edge weights. The recursive net is similar, but you can see in this example that there's one point where 2 hidden states outputs are merged and fed into one. This is caused by the sentences being interpreted not as sequences, but as hierarchical trees. Because every sentence has a different tree, every training sample has to be trained differently, and this is what makes it a bad fit for TensorFlow. In addition, Kanta is replacing the identical edge weights connecting hidden states with 46 sets based on the dependency relationships, and every hidden state is being trained on the correct answer for the quiz bowl prompt rather than the next word in the sentence. So no TensorFlow replacement for the recursive neural network, but plenty of other ideas to try, as you'll hear about next.
So for the final project, I looked at word vector representations which could replace word2vec in the current model. I looked at global vectors for word representations and fast text, and I also looked at a post-processing step which could be used to improve the quality of the word vectors. So the word2vec model uses the nearest neighbor metric, cosine or Euclidean, for calculating how closely 2 word vectors are related. This model believes that vector differences are a better metric. This intuition comes from the word analogy test. A standard example of a word analogy test is, if man is to woman, then king is to what? The way that this is calculated is first the king vector is subtracted from the man vector, and then the woman vector is added to the total. So what this says is that some meaning can be represented by the difference between the man vector and the king vector. So after doing some linear algebra steps, which will be explained in the paper, the word vector differences can be captured using the probability of k given word 1 divided by probability of k given word 2. Here, k given word 1 is word 1 occurring in the context of k. This can be pre-calculated using the co-occurrence matrix. Now moving on to model details. The co-occurrence matrix is calculated using the n-gram sliding window method. For my implementation, I limited the context to 10 words. Weights in the co-occurrence matrix are the inverse of the distance between the 2 words. The cost function is the weighted least squares problem. Here W is the word vector and W tilde is the context word vector. Bi and B tilde are biases. Xij is the co-occurrence matrix and the log here captures the vector differences. Fxij is the weighted function, which has the property that it vanishes when the argument goes to 0, and when xij gets really large, it doesn't go too large. This is done so that common words such as of and the are not given a high weight. The weighted function used in the paper is shown here. Alpha is chosen as 3 by 4 and xmax is chosen as 100. The weights are trained using the adaptive gradient descent algorithm. Next is the fast text model. This model was developed by Facebook and is used for text representation and classification tasks. It's derived from the skipgram model and it tries to capture subword meaning. This model learns character level representations and then calculates word representations by summing up these previously learned character representations. For this project, the implementation provided by Facebook was used and trained on the Quanta dataset. The next thing I wanted to talk about was retrofitting word vectors with semantic lexicons. This is a post-processing step which is used to improve the quality of word vectors. The lexicons used here are WordNet, FrameNet, and the paraphrase database. So in this algorithm, lexicons are first represented as undirected graph, and then the existing word vectors are updated to their new values by using that update step. I will discuss the math behind this in the paper. According to the authors of the paper, this model is quite fast and it beats the current state of art methods in semantic evaluation tasks. For the results, the base existing implementation gave me around 57% accuracy, and when I used the FastText model with retrofitting, I got around 59%, and the FastText model and just the FastText model gave me around 58%. I haven't gotten the results for the glove model yet, and I will include them in the paper.
So for the next phase of the project, we wanted to look at alternatives to logistic regression as a machine learning algorithm for the natural language processing. So all during this semester, we had seen logistic regression appear when we were trying to do natural language processing in the homework or in the spam versus ham examples. And then again in this paper with the quiz bowl, we saw logistic regression was used with the features that were output by the RNN. So we wanted to investigate alternatives to logistic regression. Some other algorithms that we looked at are ones that we saw during this class in machine learning, like naive Bayes, support vector machines, AdaBoost, decision forest, and k-nearest neighbors. So the results, when we look at the results, we can see that nothing was able to beat logistic regression as far as its accuracy on the test data. A lot of the algorithms were able to get very good results on the training data, close to 100%, but then on the test data, most of them are around the 30 and 40 percentile of accuracy. So we can see that they suffer from overfitting, making strong assumptions about the data that they were trained on, and not being able to adapt enough when they see the test data. So some good performers besides logistic regression were k-nearest neighbors. You can see it had about 48.6%. That's with one neighbor. And then the linear kernel and the support vector machine had about 43.8% accuracy on the test data. Those were the best two besides logistic regression. We also looked at decision forests, and it's also important to note naive Bayes wasn't able to get that to work with the data in this case. You can see the graph here, the blue representing the percent accuracy on the training data, and you can see most of the algorithms had very high accuracy on the training data, the holdout set, but then when they were tested on the test data, most of them did decent, but then not as well as logistic regression. So why is that? So some things we can think about are logistic regression is a discriminative model, and it's able to learn the best weights for the different words or the different features in the sentence, and it's able to do that through the stochastic gradient descent. And it doesn't make as strong assumptions as the other models did, and that's why they were prone to overfitting. So all in all, what we can conclude that we learned from this is that logistic regression is indeed a very good algorithm for natural language processing, and that, as we saw in the different results from these tests, that no other algorithm that we studied in class was able to beat logistic regression in this natural language processing.
Hi there, my name is John Lammie. For this project, I decided to implement a different kind of optimization algorithm in the attempt to find a better global optimum. So for neural nets, we usually have backpropagation. So it goes over your node, finds all the gradients. But the gradient descent does have problems, such as it can get stuck, find only local optimum. It requires hyperparameters, which usually makes it so that you have to have some sort of metric that slows down the jumps as time progresses. And also it can be very computationally intensive for very high dimensionality. So I want to try to use a different algorithm that can aim for faster convergence and hopefully find the better optimum. First, I'll talk about the original setup. So this is the situation that the program had in place before I went and tried to implement a new algorithm. So first they had a standard forward propagation, but they did a funny way of finding error. So it ended up being 78% of the computation for any given update. And then they have a back propagation at about 11%, L2 regularization, and they use Adigrad, which I'll talk about in a little bit. But what that essentially does is allows them to find gradients on subsets of the data and then update the gradients across the whole feature set all in one pass. And then you have your update weights, which is instantaneous assignment. Adaptive gradient algorithm, or Adigrad, was the algorithm they used in this paper to compensate for such a large feature set. So it's online, performs better on these high dimensionalities. They do L2 regularization before they send it to Adigrad. And just to give you a comparison, the feature set on this algorithm is almost 2.5 million features. So incredibly large. Normal gradient descent does not work very well. So the performance of this algorithm is actually pretty good. For 73 minutes of run on 6 threads on a fairly fast CPU, get training accuracy of 98, but you can tell it overfit because the validation set's only 43. So the algorithm I wanted to implement was particle swarm optimization. It's based on swarm intelligence. And what it does is it has every little particle has its own state. So it has its own location and a velocity. So what it does is on any given step, it updates its velocity, randomly moving around, but at the same time, in a spring fashion, moving towards not only its personal best, but a global best found among the swarm. PSO, particle swarm optimization, has many strengths that made it appealing for this program. So it's less likely to get stuck in local minimum. But gradient descent, you always are simply going down. But because of the modifier used to calculate jumps, it's able to make particles jump out of local minimum, especially if there's a global best that's far away. This also can help you when you're really close to a global best. So instead of oscillating around, you're really close, and so your jumps are really small. It's highly parallelizable. You can send off chunks of the swarm on different clusters and processes, and they can run independently with only a single parameter needing to be updated across the whole swarm. Reduces the need for complex post-processing and calculations. There's no L2 required. There's no fancy wrapping or unwrapping that you need to do. You simply give it an error and its parameters, and it should be able to optimize against that. And it's easy to implement. As you can see from the algorithm above, that's essentially the whole algorithm. So you have your velocity that's updated by chi, which is essentially a velocity dampener of sorts. You have your old velocity, you have a random variable, and then you have your difference against what your personal best and the difference against the global best. So in a combination of your personal best and global best distance away from that, you randomly move towards it and modify your past velocity. And then you apply that to your current spot and essentially make your jump. Weaknesses, though, it requires more memory. So in this instance, we have feature sets of 2 million. So every particle has its own instance of that feature set. It doesn't prove to converge. There's no real math behind it that would show perfect convergence after some eventuality. It does have hyperparameters still, but there are some good defaults since the particles act kind of like springs. There's good general bests that you can use that help. And there's no way to determine how many particles to use. So you can use 10 particles, 20, 2,000, 1,000. There's no real well-determined usage. So for my implementation, I just generated an error over the whole data set for every particle. So this was good because all particles need to have the same information. If one particle finds global best, it should be relevant to the others. If they don't have the same data, they're not getting the same errors, and the global best doesn't make any sense. Bad, though. It's very costly. As you can see in the previous slide, the forward propagation was the vast majority of the computation, but I'm replacing the back prop, which was only about 11%. So instead I end up replacing 11% with almost 1,000%. Each particle has to then do another forward prop. So if forward prop is cheaper, we might have better convergence. Also, I kept running a memory error. That 2 million feature set for X amount of particles uses up the 4 gig memory space allotted for a 32-bit Python very quickly. And in this situation, it fails to optimize. So possible reasons are feature sets have too little power. Having 2 million and you oscillate one a little bit, so it's not going to update properly, and some others might cancel it out. So there's no one feature that it would detect movement on. It requires too many steps. So usually you want to do a lot of steps on each particle, but due to the cost of Running forward prop on each particle, you end up spending far too often just waiting for it. It just takes far too long. The way the feature set was designed, it was essentially 3 different feature sets wrapped into one long one. So there was some dependencies in there that particle swarm optimization doesn't necessarily touch. So as a conclusion, PSO doesn't really work in this one not as well as hoped. So yeah, forward propagation was far too expensive. Feature set doesn't reduce very well, so you have to use that full 2 million feature set every single time. So future work would be reduce forward prop, make it so that that's the least costly thing possible. So essentially you would change the error metric. Right now it's making it so it makes sense to humans, but the algorithm doesn't care. So if we just do something that gradually minimizes, it might be far less costly. The 64-bit version of Python might work better. And also you might want to reduce the size of each particle in some way. And finally, use multiple swarms. Instead of having one global best, you have multiple global bests, essentially swarm squads, which go across the sample space. It might be better so that the global best still makes sense within each group, but it's able to work on subsets of the data, and then we'd have to find a way to merge those global bests together. So it's a nice algorithm, but it seems like it needs a little more tweaking to work on such a large feature space problem.
Hello, my name is Akshay, and my part in this project was to do feature engineering to get the best possible results using the data we have and then compare it with the results from Quanta. So when we first read the paper, it was observed that the authors of the paper just used a bag of words approach as a baseline model. So I wanted to find out how the model will do when features more complex than a simple bag of words are used as input. I also wanted to find out how the model would do when traditional feature engineering approach is taken as opposed to automatic feature extraction using RNN. So first I did pre-processing in which I removed stop words and the characters were all converted to lowercase. For the features, I used bag of words count. Bag of word count was an obvious choice because certain keywords would give good information gain for an answer. So a bag of word count was used. Word bigrams. So word pairs are some certain word pairs are important in the question, which would give the most information gain for an answer. So word bigrams were used. Character engrams for n equal to 1 to 8 was used, which gave significant information gain. Apart from that, latent semantic analysis on word tokens was used and features extracted from that were used in the model. So latent semantic analysis helps in analyzing relationships between the set of documents and terms they contain by producing a set of concepts related to the documents and terms. So when used, I saw the accuracy increase significantly, so I kept this feature. Apart from this, named elements extraction was used as certain questions would contain important names which would indicate towards the answer and would give the most information gain. Other notable features tried but no improvement was observed were part of speech tagging for nouns and adjectives, checking for an integer in the question. So in certain questions I noticed that there were years in which some certain event was happened. So I tried to get that feature, but it didn't really work out for me. So other than that, word trigrams were used and were tried, and count vectorizers, hashing vectorizers for bag of words, character engrams. So our model performs decently well as compared to Quanta's RNN model. Our model achieves an accuracy of 57.7% as opposed to 60.2 from Quanta's results. It can be seen in this graph that our model doesn't do really bad as compared to Quanta and does really well as compared to bag of words or bag of words decision tree model. In this graph, I have shown the accuracy for each sentence position for each model. For conclusion, our model outperforms bag of words model by 61.6%. Also, our model outperforms bag of words decision tree model by 22%. But Quanta outperforms our model by 4%, which is not a lot actually, when computation time is taken into account. So basically we have a trade-off of computation time versus accuracy. Quanta's RNN takes close to an hour to generate these features, while our model generates features within a minute from the same dataset. So our model is a quite cost-effective model with decent performance. Apart from this, I also built the baseline model. The baseline model for the project takes in all the complete question for generating an answer and not single sentences, and it achieved a 54% accuracy score, and it used bag of words features.
So to review, we looked at TensorFlow porting, word representations, answer prediction models, particle swarm optimization, and feature engineering. We had planned to try combinations of the ideas that had improved accuracy, but instead we made a lot of progress at eliminating some weaker alternatives. Thanks for watching.